Yes, welcome once again. This is 300 Plus Academy, and it's time to take a dive into the beautiful world of chemistry. The last time we had chemistry, we looked at introduction to chemistry, and as well, we touched on scientific method, being that chemistry is an investigative science. So, quickly today, what we'll be looking at is matter and energy, more specifically, kinetic theory of matter, talking about physical forms of matter, solid, liquid, and gas. So, without much ado, let's get right into it. So, since chemistry is the study of materials or matter, the next sensible question you should ask is what is matter or material? Well, when you say matter or material is just about anything I see, anything I can feel, anything I can touch, even when I cannot touch it, if I can feel it, if it occupies the space where I am, then that is a material or matter. So I said matter is anything that has mass. If it has mass and it occupies space, talking about volume, then that is matter. So chemistry is the study of materials or matter, and matter is anything, just about anything that has mass and occupies space. Now, talking about the various forms of matter, or what rather state of matter that we have in classifying matter, there are two approaches to this. If it is based on physically what I can see around me, matter fits exactly into the category solid, liquid, and gas. Of course, for example, this is looking solid, this is looking liquid, and of course, the air around me, that's the gaseous state of matter. And then there is a fourth state which talks about the plasma. Yes, as you will see on your screen, or much later, I'm going to display what plasma is on your screen. Let me see if I can display that now. Let me quickly see. So, and then of course, there is a fourth state known as the plasma state of matter at very high temperatures of the sun and the stars. The combination of electron and the nuclei of an atom combined together is what is known as plasma. We'll talk about that much later. You'll see it on your screen much later. But this is it. When you talk about the state of material based on physically what we can see, we classify matter as solid, liquid, and gas. That's based on physically what I can see. But there is another classification, and that classification is based on composition. I'll talk about that later. But for now, the thing is, matter is anything that has mass and occupies space. And then we want to talk about the states of matter, but I'm coming back to that. Okay, moving on. The next thing that we need to note before we proceed with this topic, talking about matter and energy, is what we call kinetic theory of matter. According to kinetic theory of matter, all matter or materials are believed to be made up of tiny or discrete particles, which tells me that matter is not one whole. Take, for example, this water now. If you think it is just one whole, look at it. If I open this and I took a gulp, now the way I'm going to see it from the chemistry standpoint is I took in some particles, leaving behind some other particles. So that automatically tells me the water you see here is not one whole. I'll give another example. Let me use my meter rule here. This is a rule which is made from wood. If I get my saw and I decide to cut through this, I'm going to have wood dust, wood shavings. Now, just because I'm cutting this into two, now I'm having wood dust. Now, the particles that make up this meter rule now are those wood dust. telling me that this is not one whole. This is made up of what? Particles bounded together by what we call intermolecular force. The water that I have here, is not one. These are particles bounded together by intermolecular forces. And that is what kinetic theory of matter is trying to explain to us, that any matter that we see, we need to accept that it is made up of tiny particles. And those particles, like it or not, are in constant motion. And of course, anything that moves is able to move, is able to exhibit motion simply because it has kinetic energy in it. In other words, it has heat energy. Some will say, how do I mean that every material is constantly moving? Take, for example, get your ears here closer to the wall. To tell you it is made up of particles, you will feel the vibration, telling you that the particles looks as though it is not moving, but chemistry-wise, the particles are moving. Only that the particle, let's say this wall now, the particles only vibrating about a fixed position. So the thing is this: we are studying matter in chemistry, and matter is just about anything so long it has mass and occupies space. And according to the kinetic theory of matter, any material that we see is made up of tiny or discrete particles. Let me take in some particles again, telling you that this is not just one whole. It is made up of what? Tiny or discrete particles, and those particles are in constant motion, and therefore they possess kinetic energy. If they are in constant motion, they possess kinetic energy. That's the first thing you need to understand about matter. The second thing you need to understand about matter is that particles of matter are held together by intermolecular forces. I explained that. Now I have particles of water here. What holds the particles of water together? Yes, the molecules of water together in this case is what we call intermolecular forces. Let's say H2O is water. Okay, what holds this H2O to this H2O? There is an intermolecular force here, and that is what we want to talk about. Actually, there are about two types of intermolecular forces. We have cohesive force, and then we have adhesive force. That's cohesion or adhesion. Now, talking about cohesive force is the force between molecules of the same substance. Yes, is the force between molecules of the same substance. And then adhesive force is the force between molecules of different substance. Take, for example, this is a plastic, and then I have water in it. Now, the force between water molecules here, let's say I have H2 and H2 here, because they are of the same substance, that is cohesive force. But between the water molecules, that's the particles of water, and this plastic, or let's say this Pyrex glass, for example, between this water and this glass now, that is what we call adhesive. Between this water and this glass, that is what we call adhesive force. So cohesive force is the force between molecules of the same substance, and adhesive force or adhesion is the force between molecules of different substances. I want to dwell more on this intermolecular force, but take note, I said for us to understand matter very well, there are two things we need to understand. We need to know very well about kinetic theory of matter and what it states. It simply states any material that I see is made up of tiny or discrete particles, and those particles that make up those matter are in constant motion. And since they are now in constant motion, it means they have kinetic energy or heat energy in them. And then we talk about intermolecular forces, which are the binding forces holding particles together. If you're talking about particles or molecules of the same substance, then that is force of cohesion, that's cohesive force. If you are talking about particles of different substance, like you can see here between water here and the glass vessel, that is adhesive force. Now I want to dwell more on this. When you talk about water and glass, what you have here, just at the edge here, for example, this is glass, and then you have water in here. You see the force between the water in here and the glass here is adhesive force. And the one between water molecules H2O and H2O is cohesive force. But the thing is this: have you noticed that water is usually concave to here? Is usually having what we call a concave meniscus. Concave meniscus. It's usually having a concave meniscus. Why is that? It's very simple. The thing is this: you are looking at a balance between two forces here, cohesion between the water molecules, and then you're looking at adhesion between the water and the glass. But the thing is this: the adhesion, that's the force between water and glass, is greater than between the water molecules. The force of adhesion between water and the glass is greater than the cohesion, that's the adhesion here between water and glass, is greater than the cohesion between water molecules. Look at it. And that is the reason why water is having a concave meniscus to air. It's concave to air because adhesion there between water molecules and the glass is greater than its cohesion, so that the glass has more pull over the water and is pulling it, whereas the molecules of water in here doesn't have much pull as that of the adhesive force. So that is why water is concave to air. But then when you talk about mercury, mercury in this case is convex to air. It's convex to air. And when you, let's say, okay, I want to talk about mercury. If this is a capillary tube, okay, if I have this here, this is the shape that mercury is going to, this is the shape that mercury is going to have to hit. Very simple. It is not pulled towards the glass, but it is rather pulled inwards. It is pulled inwards. And the reason is very simple. You see the shape? You see the shape? It is pulled inwards. And the reason is very simple. In the case of mercury, the cohesive force that's between Hg and Hg. Hg is the formula for mercury. The cohesion between mercury is far greater than the adhesion between mercury and glass. And that is why for mercury, it is always having a convex meniscus to air, because Hg particles have a stronger attraction to each other than to the container. Also, take note, since the glass is having a stronger pull for water than between the water molecules, that is why if you put a narrow capillary tube into this trough of water, the water will rise because it is being pulled by the glass. So we say water rises in a capillary tube. The reason is because adhesion is greater than cohesion. Remember that capillarity is the tendency of a liquid to rise or fall in a capillary tube. So when you look at the case of water, water is going to rise because the adhesion is more than the cohesion. And in the case of mercury, the reason for this is because if you place a narrow capillary tube here, the mercury level will fall because the mercury has a stronger cohesion than adhesion, is more pulled towards another mercury particle than it is being pulled or attracted towards the glass. But the point is this: for mercury, it falls in a narrow capillary tube and it has a convex meniscus to air, simply because the cohesion, as the cohesive force, is greater than the adhesion, that's adhesive force to the glass. But in the case of water, it rises in a narrow capillary tube because the adhesion to the glass particles here is more than the cohesion between the water molecules. That ends that. And of course, I've seen a JAMB question like that before. Take for instance, if I say, oh, I have Naira notes. Let me demonstrate that I have Naira notes. Yes. Let me bring out clean Naira notes. Okay, I have Naira notes. Now, if I take some moisture here, simply because I want to count this, the force between this moisture and the Naira note I'm counting is what? Of course, they are particles of different substance. They are molecules of different substance. That is going to be adhesion. That's a direct UTME question. Don't forget that. So basically what we are saying here is that we want to study matter because that is what chemistry deals with, and that matter is anything with mass and that occupies space. And of course, before we can understand matter very well, we need to first of all accept the fact about kinetic theory, which states that any material that I see, I need to understand that it is made up of tiny or discrete particles, and those particles are in constant motion and therefore possess kinetic or heat energy. And also, you need to understand that particles are being held together by what we call intermolecular forces, which are of two types: cohesive force between molecules of the same substance, adhesive force between molecules of different substance. So that explains that about that. Now, I want to move more specifically into the classification of matter. Talking about classification of matter, when you talk about matter, when you talk about matter, when you talk about matter, based on physically what I can see, that's based on physical form, I am going to classify matter as solid, liquid, gas, and of course plasma. But based on composition, what materials are composed of. If it's based on physical form, of course, this is solid. This here is liquid. The air around me is gas, and then at the very high temperature of the sun and stars, combination of electrons and nuclei is what we call plasma. So that is based on physically what I can see. But based on composition, when you say composition, you're looking at, okay, what is something made up of? Based on composition, any material or matter that I see is going to be either elements, compounds, then mixtures. Yes, elements, compounds, or mixtures. And don't forget that according to kinetic theory of matter, it says that materials, any material that we see is made up of tiny or discrete particles. So what are the particles of matter? In the case of elements, elements are made up of atoms. Compounds are made up of, if covalent, it is made up of molecules. It's made up of molecules. If ionic, it is made up of what? Ions. That's if it's an electrovalent compound, it's made up of ions. And when you talk about mixtures, mixtures made up of atoms, molecules, ions. But the thing is this, when you talk about the particles of matter, you're talking about atoms, molecules, and ions. So when you look at these atoms, molecules, and ions, you may want to view it from the qualitative and quantitative perspective. When I say qualitative approach, when we approach this qualitatively, what you want to talk about is, you want to talk about the atomic theories. You want to talk about atomic theories. You want to look at Thomson's model of atom. You want to look at the work of Eugene Goldstein. You want to look at Rutherford's model. You want to look at the contributions of the various scientists: Chadwick, Moseley, Giga, and Marsden. You want to talk about Dalton's atomic theory, of course, which most of them had actually been modified. You want to look at things like Bohr's model of an atom. You want to look at quantum numbers. You want to look at orbitals. You want to look at electronic configuration under the qualitative approach of matter. Then under the quantitative, there's quantity approach. Under the quantitative approach, under the quantity approach, you want to look at matter from the perspective of mole concepts and the work of Amedeo Avogadro, talking about Avogadro's number. Avogadro's number. You want to look at things like stoichiometry, and you want to look at some things like limiting and excess reactants. So basically what I'm trying to say is that when you try to classify matter or material, based on physically what you can see, you're classifying as solid, liquid, gas, plasma, which is what we're going to deal with today. But based on composition, you want to talk about elements, compounds, mixtures. Under mixtures, you want to talk about separation techniques, at least about 14 of them. You want to look at the elements you have. You want to look at things qualitatively so that you know, and this is actually the backbone of chemistry, because for this, your balancing of equation is in here, your bonding is here, and you just must understand to really be able to have a strong hold and control in chemistry. Here, you want to deal with calculations in chemistry, which I think we are going to be doing in this year, before this year 2023 passes out. Okay, so that's just that about that. Here you want to talk about your gas laws: Boyle's law, Charles' law, Graham's law, Gay-Lussac's law, Dalton's law of partial pressure, and all of that, relative vapor density, and all of that. But that's just in a nutshell what the matter we're trying to study in chemistry is like. So based on physical form, this is what we have. Based on composition, this is what we have. We head this direction, we head this direction, and at the end we are going to have a well grounded knowledge of what chemistry is about. Moving on. Looking at the various states of matter that's based on physical form. When you talk about solid, we already agreed that any material we see is made up of discrete particles. So it means if this is a solid, the particles are packed or held tightly together. So the thing is this: talking about solid, the particles are held together by strong cohesive force. So because they are being held together by strong cohesive force, the particles are held closely together, and the particles, since they are held closely together, we can tell the shape. They have a definite shape, and you can tell the space that they occupy. They have a definite volume. That is why when you talk about solid matter, we say they have definite volume and definite shape. Why? The cohesive force holds the particles together such that we can tell the shape, and of course we can tell the volume or the space that they occupy. Also, since they are being held together by strong intermolecular force, that's cohesive force, the particles are not allowed much movement. They are not allowed to move freely. The only thing particles of solid can do is to vibrate about a fixed point. That was why I said you put your ear as against the wall. What you can feel is just vibration and not more than that. Solid particles are held tightly together by strong cohesive force. As such, they are only capable of vibrational motion only. Movement is restricted because of the strong cohesive force. So since they do not have the freedom to move, they are held tightly together, it means the kinetic energy is going to be low. That is why we talk about solid as having low kinetic energy. And since the particles are tightly packed together, are densely packed together, they are incompressible. When you compress the particles, into what space do you want to compress them? Into what space do you want to push them? So when you talk about solid, solids are incompressible. The particles are incompressible. Moving on. to liquid. From solid to liquid, we can see now that the particles are a bit pushed out, they are a bit free. So the thing is that you see particles are moderately free. The cohesive force now is a bit relaxed. So we have moderate cohesive force such that the cohesive force in liquid is less than the cohesive force in solid, and the implication of that is that the particles are now moderately free. But the thing is this, when you talk about liquid, the particles are free just enough to give it a definite volume, but not enough to give it a definite shape. What liquid does is that they take the shape of their containing vessel. Looking at this water now, the shape is cylindrical. The water in here is going to take that cylindrical shape. If I put the liquid in here into a cone, like shape, you see the water is going to take this shape as well. The water will take this shape. So the thing is this, the cohesive force in the liquid is just moderate, and it allows them a bit more movement, free movement by the way, such that what it confers on liquid particles is definite volume. We can tell the volume, but talking about shape, they do not have definite shape. They only take the shape of their containing vessel. Since they are, a bit more free now, and the cohesive force is a bit relaxed now, liquids have the capacity to rotate within space available to them. Look at this now. I could swirl this round, and you see the liquid rotating within space available to them. Another thing is, you see, rotate within space in the vessel. They are capable of rotational motion. Liquid could bob up and down. You see, liquid could bob up and down. That is translational motion, when the particles just bobs up and down. Translational or rectilinear motion. Why are they able to move more? Because the cohesive force is now a bit relaxed, is not as strong as what you have in solid, so they have more degree of movement. Since they could move more, by the way, it now means that their kinetic energy is more than what you have in solid. So we say moderate kinetic energy. And the thing about liquid is that they are incompressible. You cannot compress liquid. If you try to compress liquid, you'd only displace your volume of the liquid. Take, for example, if this were to be water, and this is the level of the water, L1. If you dip your hand in here, let this be okay. If you dip your hand, the water particles, the water molecules staying here will just vacate this space for you, and they will come here, so that it looks as though the level of the water had increased. No, it had not increased. What happened is that the water occupying this space at that time had left this place, so that your hand can now occupy here, and those water molecules are now staying here. So you did not actually compress it. No, you only displaced the volume of your own hand off the water. So liquids are incompressible. You cannot compress them. Moving to gas. The gaseous state of matter, you can see the particles are very farther from each other. They are free to move. The cohesive force here is virtually non-existent. It's extremely low, negligible, as you see in some textbooks. Zero, that's what they said in some textbooks. So the thing is this, the cohesive force is non-existent virtually. So therefore, the particles are completely free to move in any direction. You can see random motion, non-directional movement. They just begin to move in just about any direction. Hence, when we talk about gases, since they are able to move, nothing is holding them back, nothing restricts them, nothing pulls the particles together. They do not have a definite shape, and they do not have a definite volume. And since they are now, very free to move because the cohesive force is non-existent, they have very high kinetic energy. Of the three states of matter discussed so far, gases are the most energetic of these three states. You can see here, kinetic energy very high. Kinetic energy in gas is greater than what you have in liquid, and is then greater than what you have in solid. Since we have more than enough space in between the particles, they are compressible. I could push this into the space. 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 I could push into the space. When you push your liquid, this is what you're going to have. Imagine bringing those particles together. When you compress liquid, sorry, when you compress gases, they suddenly become liquid. You can see it is now liquid. So that is the thing. Gases are compressible. When you compress gases, they become liquid. So that is that about this three states of matter. And then you must have noticed a certain pattern talking about these three states. As we move from solid to liquid and then to gas, something is happening. You see the cohesive force is decreasing. The cohesive force is decreasing. You can see cohesive force, more freedom, more freedom. The cohesive force is decreasing. And then as we also move down, you must have noticed something. The degree of movement, ability to move, is increasing. Now, the movement invariably means they now have more kinetic energy or more heat energy. So you can see low kinetic energy, moderate kinetic energy, and then very high kinetic energy. So cohesive force is decreasing, whereas kinetic energy or thermal energy or heat energy is increasing. When one quantity increases and the other decreases, that is an inverse relationship. So what that means is that I can come here and say, as I move from solid to liquid to gas, this is what I have noticed. The cohesive force is decreasing, the kinetic energy is increasing, so that cohesive force or intermolecular force is looking as though it is inversely proportional to the kinetic energy. Yes, it's inversely proportional to the kinetic energy. And when you look at that, cohesive force, this will give me a proportionality constant. Cohesive force therefore equals to a constant divided by the kinetic energy or the thermal energy. And if we are to go by this scientifically, that will mean that the product of my cohesive force and the kinetic energy is always a constant. Yes, product of my intermolecular force and kinetic energy is always a constant. That is what I can deduce from these three. And of course, recall that I talked about plasma, as you can see displaying on your screen. First, in those image displaying on your screen, you can see diagrams for solid, you can see diagrams for liquid, and then you can see for gas. Yes, but talking about take note, everything we've discussed is exactly what you have in those diagrams, but take note of the plasma. I said in there that at the very high temperatures of stars, atoms lose their electrons. Yes, the electrons become excited, so the electron leaves the atom. So in this case, the mixture of the electrons and the nuclei result in the plasma state of matter. So that is talking about very high energy state of matter, and that's just about ends that. So that the next thing we now want to talk about is how particles change from solid to liquid and then to gas. Like you can see here, I talked about gases, and for these gases, you can see that when we compress them, they immediately change to liquid, because you can now see, look at, they are farther apart before, they are farther apart here, and here they are closer, just as you have in liquid. So when you compress gas, they become liquid. So the next thing we are supposed to look at now is talking about the various change of state. About change of state. Talking about change of state, it simply means matter can change from one form or state to another depending on if it was added or removed from that material. So I said here, matter can change from one form or state to another due to the addition or removal of heat. Take for instance, if I have ice, ice is a solid. For ice to become water, liquid water, of course I must have added heat. So for solid to change to liquid, the name of the process is melting, and that is because we've added heat from a lower energy state, which is a solid, to a higher energy state, which is liquid, that's water. Now let's assume I have my liquid water and then I am trying to boil. I have my liquid water and then I eat that. I have my water and then I eat that. What happens once the liquid particles here had acquired enough kinetic energy? You see the particles begins to escape. So because why? Liquid are changed to gas. So the conversion of liquid to gas, the name of the process is evaporation or vaporization, and that is as a result of addition of it. That's why you have plus heat. And let's assume that this is happening in a closed system, in a closed situation. Now let's close this up. Let's close this up such that the liquid has become gas but not able to escape. So what happens is that by the time the liquid are changed to gas here, liquid are changed to gas, that is evaporation. If the gas particles are not able to escape such that they touch on the cooler region, which is the lid or the cover here, the lid or the cover here, if they touch on this, then what happens is that those gas particles suddenly begin to change back to liquid, and that is why when you open the lid, you see water droppings from the lid, from the cover. So the process of your gas changing back to liquid here, the process of your gas here changing back to liquid is what we call condensation or liquefaction, and that is because as the gas particles bombard the cover or the lid, the energy they were moving with is going to reduce, because this is of course much cool, and talking about solid is at a much is having a much lower energy. So if the gas particles touch on the lid, they are going to change back to liquid. So the process of gases changing back to liquid is what we call condensation or liquefaction. Of course, your liquid can change to solid. If you put, let's say, water into your refrigerator, it could change to ice. So from a higher energy state to a lower energy state, that is removal of heat, and the name of the process is freezing or solidification. Of course, let's assume we have something like camphor or naphthalene, solid to gas. That's talking about iodine. The process of solid changing to gas directly without passing through the liquid phase. Without passing through the liquid phase, no, not passing through the liquid phase, is what is called sublimation. And examples of solid that can sublime, we have iodine, ammonium chloride, camphor or naphthalene. We have dry ice or solid carbon dioxide, just that you see the smoke you see. Let's say when an artist gets on stage to perform, is not smoke. That is actually solid carbon dioxide or dry ice, now changing from the solid form to the gaseous state. And of course, let's assume that we have a setup like this. Let this be my boiling tube where I have ammonium chloride here. I have ammonium chloride here. If heat is added to this, what happens is that the ammonium chloride suddenly changes to vapor, NH4Cl vapor. Okay, if it were to be in a closed system, let me plug this with a cotton wool. and the ammonium chloride vapor are not able to escape. Recall, this is solid NH4Cl, ammonium chloride, and are changed or sublime to become ammonium chloride vapor. But the vapor is not able to escape now. If it touches on the cooler region, what happens is that it condenses. It changes back to solid. So this is solid ammonium chloride. That is solid ammonium chloride, called sublimate, by the way. But then, when gas change to solid, that means from a higher energy state, which is a gas, to solid, which is a lower energy state. That is a form of condensation, but more specifically, it is called deposition. That's, it leaves us with deposits here, deposit of the vapor. So that is that about that. Gas changing to solid is called deposition. And of course, we've had instances of jam questions under change of state. Imagine you have solid, this is liquid, this is gas. If I say A, my A is going to be liquid changing to solid. You can see the arrow, of course. Liquid changing to solid, A there is going to be, of course, freezing or solidification. My B, solid changing to liquid, that is going to be melting. And of course, my liquid changing to gas, that is E. Here, my liquid changing to gas, that is going to be evaporation or vaporization. Then my gas changing to liquid, gas changing to liquid, that is condensation or condensation or liquefaction. Gas changing to liquid, condensation or liquefaction. And then look at it, solid changing to gas, C. Solid changing to gas, look at the arrow, that is sublimation. And my gas changing to solid, that is condensation, but more specifically we call it deposition. And that ends that about change of state. Subsequently, we have to find explanation, elaborate explanation to the various change of state, talking about melting when vibrational energy is greater, when its energy is greater than vibrational energy, yes, when vibrational energy is greater than the binding force. We are going to talk about evaporation, and of course, under evaporation, we have to explain how evaporation causes cooling. We have to talk about if it happens in a closed system. We have to talk about vapor pressure. We have to talk about saturated vapor pressure and consequently boiling and all of that. So we still need an elaborate explanation for the various change of state, because examination questions do come from that aspect as well, and we have to do well to leave no stone unturned. So that ends that. So the next thing we have to talk about, we have to return back to where we had actually started from. One of the core thing we talked about today was a kinetic theory of matter, which states that any material that we see is made up of discrete particles which are in constant motion and therefore possess kinetic energy. Can we prove it that materials that we truly have are made up of discrete particles? I demonstrated that using water. You take some, you leave some. So there are evidences in support of the kinetic theory of matter, which is what we are to talk about now. So wrapping this up is for us to go back to where we actually, a very important point we made at the start, and which was about kinetic theory of matter. One thing about the kinetic theory of matter is that we're able to establish that any material that we encounter is made up of tiny or discrete particles. So which means matter is not just one whole, it is made up of particles. So but we have to give evidences to back that up. Of course, that's why we said evidences for the particle nature of matter, to prove that truly materials are made up of particles. So the observation of phenomena which show that matter is made up of discrete particles include: number one, the solution of solids and liquid. When we talk about the solution of solids in liquid. Let's say if we are to have a liquid like this, and we are dropping a crystal of solid sugar, after some time you'll see the size reduces, and then the size reduces, telling me that some particle had actually left. If this were to be one whole, then it should remain continuously like this. But the fact that the size continues to reduce until everything is dissolved tells me that truly materials or matter are made up of discrete particles. Another one is evaporation of liquid. If we were to boil, if we were to eat a liquid here, we were to eat a liquid here. Now, when we eat, the particles of the liquid here begins to acquire more kinetic energy. They begin to absorb more heat energy. Then it gets to a point they break off. Some particles leave, some remains. But I think if the liquid here is just one whole, perhaps everything should have just left at once, and then we should have an empty vessel. But that is not the case. Some particle leaves, some particle remains. So you see, some particle leaves, and then some particles remain. Evaporation tells us here that truly materials or matter are made up of discrete particles. If it were not so, then everything should just have left or evaporated at once. But the fact that some particles left, some remain, is a proof that truly materials or matter are made up of discrete particles. Another one is sublimation of solid. When it comes to sublimation, let this be my naphthalene or camphor. This may be the size. I could drop it somewhere in my room after about a week, and then the size becomes this, and then the size becomes this week on. So what that means is that some particles had actually changed to gas, and that's why I can, of course, perceive the odor of that naphthalene in my room. Okay, and over time some more particles leave. So I think if this naphthalene is just one whole, maybe everything should just have disappeared. But the fact that some particles change to gas, some remain as solid, is another proof that truly materials are made up of tiny or discrete particles. Another one is diffusion of gas. Diffusion always takes place when molecules or particles moves from a region of higher concentration to a region of lower concentration. If you were to use perfume or body spray, let's say earlier in the course of the day, with time you begin to notice that the intensity of the odor of that perfume begins to decrease. Why? All through the day, as you move from one place to another, you see those particles, those molecules. The odor is actually leaving. If it were one, I think everything should just have left without me perceiving it. But what happens is that some particles have left, some remain. So diffusion of gas or perfume from a region of high concentration to a region of low concentration is another proof that truly materials or matter are made up of discrete or tiny particles. Also, diffusion of colored crystal. Let's drop a purple potassium permanganate, potassium tetraoxo manganate 7 in water. Let this be my water. Okay, let this be water. If I drop purple potassium permanganate, after a while you see it spreads. It spreads all through. It spreads all through. Perhaps you can see that on your screen. It spreads all through. The spread, diffusion of colored crystal from a region of high concentration to a region of lower concentration, is another evidence to prove that truly matter is made up of discrete particles. If it were not so, I think the color should just move from, the color is here. If the color were to be here, then if the color were to be here, then I think if the color is to be here, it should be here. If it wants to be here, it should be here. But what do we have? Some spread this way, some this way, some this way, some this way, until the color is evenly distributed. So diffusion of solid or of colored crystal is another evidence that truly materials or matter is made up of discrete particles. Osmosis is another one, as you can see on your screen. Osmosis is movement of water from a dilute solution into a more concentrated solution through a semi-permeable membrane. As you can see on your screen, I think if the water there is just one, then everything should just have left solution A into solution B. But what do we have? Some just left, some left. So telling you that the water is not one whole, but it is made up of particles. Some particles left, leaving behind some other particles of water. So osmosis is another proof that materials or matter is made up of discrete particles. Another one is Brownian motion. Brownian motion is the non-directional or random movement of particles in a fluid. Take, for example, smoke particles in air. When you have smoke particles in air, what happens is that to tell you that those smoke particles, they are not just one whole, but they are discrete particles. You see some particles move in this direction, and then some particles in this direction, and then some particles in that direction. That's, we're talking about haphazard movements here. Haphazard movement, and that is when you see those particles, you see they just move, various particles moving in various directions. Look at it, random movement of particles in a fluid. Smoke particles in there, some particles move here, some particles here, some particles here, some particles here, and then some particles here. So the fact that these particles are not moving in one direction is a proof. If those particles are one whole, then I think they should just have moved in one direction. But what do we have? Some particles move this way, some move this way, telling you that truly materials or matter are made up of discrete particles. Also, when we view pollen grain in water, the movement, it proves to us that when viewed with a powerful microscope, it's a non-directional movement. It proves to us that truly materials or matter are made up of discrete particles. Also, dilution of colored solution to give yes, to give a solution which are lighter in color. Imagine dropping liquid ink into water. That's what we are talking about. It's a colored solution, but when we drop it in water now, it's going to be light, telling you that it had spread. It is not one whole, and these are evidences for the particle nature of matter. So with that, we've come to the end of this topic, talking about matter and energy, kinetic theory of matter, and as well change of state. Quite a handful, but we've been able to get that done and dusted with. So don't. So that is that about that. Quite a handful. We've been able to talk about matter and energy. We've spoken about kinetic theory of matter. We've looked at change of state and quite a number of things. Do not forget to subscribe to this channel, turn on the notification so that at each time that we upload lecture content, you get notified and you can breeze through things. Also, do well to share with your peers. They will be happy you actually did that for them. From myself and the entire team here, it's bye for now. Thank you.